Hello everyone, this is Dr. Captain K. Sujata, Professor of Mathematics, St. Joseph's College for Women, Autonomous, Visakhapatnam. In this session, I am going to discuss Cayley-Hamilton theorem, that is a first part. Cayley-Hamilton theorem, entire on main thing is Cayley-Hamilton theorems. Two types are there. First one, Cayley-Hamilton theorem on matrices, and the second theorem is Cayley-Hamilton theorem on linear operator. Right? No, here we are given the Cayley-Hamilton theorem. One means only two theorems I am going to explain in this session, in this video. Whereas the Cayley-Hamilton theorem is two also there. So I am going to do the problems. I have discussed all the problems on Cayley-Hamilton theorem in that video, two video. Right, now coming to the next one. These are my details. After this session, if any doubt, you can contact through my email ID. Now, course outcomes. After successful completion of this course, the student will be able to know and apply the principles of linear algebra, know vocabulary, notation, and operations for matrices and vectors. Find the characteristic equation, characteristic values, and characteristic vectors of the matrix. Apply Cayley-Hamilton theorem to the problems for finding the inverse of a matrix and higher powers of matrices without using routine methods. What is a routine method for finding the inverse? A inverse is equal to adjoint A by det A if det A is not equal to 0. That is a routine method. Without using that method, by using the Cayley-Hamilton theorem, easily you can find out the A inverse. Now, in the previous sessions, we have discussed following topics. Definitions on characteristic matrix, that is matrix A minus lambda I, characteristic polynomial, determinant of A minus lambda I, characteristic equation, determinant of A minus lambda I is equal to 0, characteristic root, what is meant by characteristic root? Lambda, in the characteristic equation, lambda we call it as a characteristic root. It satisfies the characteristic equation A minus determinant of A minus lambda I is equal to 0, and the characteristic vector. For every characteristic root corresponding, there exists a characteristic vector, that is x, satisfying the equation, the non-zero vector x, such satisfying the equation Ax is equal to lambda x, then x is called the characteristic vector. Some theorems on characteristic roots and characteristic vectors of a square matrix and linear operator. Procedure to find the eigenvalues and eigenvectors of a matrix. Problems on eigenvalues and eigenvectors of a matrix. And we have discussed all these things. Some identities on, that is the last video, I have discussed some identities on eigenvalues and eigenvectors of a square matrix. These are the topics I have discussed. Now coming to in this video, so what we are going to discuss. So in this video, I am going to discuss about the theorem. Very important one, Cayley-Hamilton theorem on matrices. Cayley-Hamilton theorem on matrices. And another theorem is there, Cayley-Hamilton theorem on linear operator. Right? Now this is a statement. Every square matrix satisfies its characteristic equation. Now take any square matrix, satisfies its characteristic equation. So what is meant by characteristic equation? If we take the square matrix as A, so A determinant of A minus lambda I is equal to 0. Right? Now here we are considering the square matrix as n by n of order n matrix, that is n by n square matrix or n-rowed square matrix. So let A be the square matrix of order n by n. Means this is a square matrix of order n by n. Always square matrix is in the form of A. Capital A is equal to n by capital A is equal to Aij n by n. Aij n by n, we call it as a n-rowed square matrix. Aij means I rows, j columns with the degree order is n. Right? So these are the I rows, means rows are total number of i's and columns are total number of columns. Aij n by n. So this is the rows and the n rows, n columns totally. So in this we are representing Aij n by n, right? Now in this, after taking the A, we have to consider characteristic equation of A. So always characteristic equation is determinant of A minus lambda I is equal to 0, right? Now what is the determinant of A minus lambda I? In the diagonal matrix, in the diagonal elements we have to subtract lambda value, right? That is A11 minus lambda, A22 minus lambda, and so on, ANN minus lambda, this determinant equal to 0, right? Now expansion of this determinant, this is a n by n matrix, no? So we'll get the this is a characteristic equation is in the form of nth degree in lambda we will get. So that's why, so after this expansion directly we are taking the nth degree polynomial, and also here we'll get minus 1 minus is there, no? That's why all lambda values are negative, no? That's why we are taken minus 1 whole to the power of n is a common into this is a polynomial in terms of the lambda, nth degree polynomial. So we are considering nth degree polynomial lambda to the power of n plus p1 into lambda to the power of n minus 1 and so on. Constant term is pn. This is a nth degree polynomial. If we equate to 0, we'll get the characteristic equation of nth degree in lambda, right? Now this is the, but minus 1 whole to the power of n is not equal to 0, so that this polynomial becomes a 0, right? This expression becomes a 0 in terms of the lambda, right? Now what we want to show, this is nothing but characteristic equation. This is nothing but characteristic equation. What is our statement? Every square matrix satisfies its characteristic equation. So we got the characteristic equation. What we want to show, that square matrix we have to substitute in place of lambda in the characteristic equation. Means a to the power of n plus p1 into a to the power of n minus 1 plus p2 into a to the power of n minus 2 and so on, plus pn is equal to 0. So we want to prove that this condition. For proving this condition, we are going to write some known identities, some known formulas. So what is the first one? The elements of the matrix. The elements of the matrix A minus lambda I. Matrix we have taken A minus lambda I. So in this elements, what type of elements? Their degree is at most first degree. So at most first degree of these elements. Elements of the matrix of degree is at most 1, right? So the cofactor, after that using this, the cofactors of the elements are at most n minus, because this is a polynomial, we got characteristic equation, we got nth degree, no? Automatically, and nth degree from where we got it, from the matrix A, because A is the order of A is n by n. So if the matrix A is n by n, so from that matrix we'll get the cofactors of the elements are at most n minus 1 of n minus 1th degree in lambda. Cofactors of the elements are at most n minus 1th degree in lambda, right? Now, therefore, using this, we can write down the adjoint of A minus lambda I. So after getting the cofactors, after defining, so this is the cofactors of the elements, what we got it, n minus 1th degree in lambda. So using that, adjoint of A minus lambda I can be expressed as a matrix polynomial in lambda. This is a matrix polynomial in lambda. This is a polynomial of degree n minus 1, of degree n minus 1 in lambda. Therefore, take that polynomial of n minus 1th degree. Right? Adjoint of A minus lambda I can be written as B naught into lambda to the power of n minus 1. This is a degree is n minus 1. That's why maximum degree is n minus 1 here. Lambda to the power of, we are going to start with the lambda to the power of n minus 1. No, this is a constant term we have taken. B naught, B1, B2 and so on. Bn minus 1 are all n by n matrices. Right? No, this is a by matrix condition. By matrix theorem, matrix condition, A into adjoint A is equal to det A into I actually. A into adjoint A is equal to det A into I. But det A into I is nothing but det A, no? So only simply we have taken det A. So this is a standard statement. We have to remember A into adjoint A is equal to det A. Right? Now we are replacing A by A minus lambda I. We are replacing A by A minus lambda I. So we are substituted in place of A minus lambda I. In place of A, we have substituted A minus lambda I. right? In place of A, substituted A minus lambda I. Now after that, now substitute what is already we have taken. Adjoint of A minus lambda I is n minus 1th degree polynomial. We substitute this value, and also we know determinant of A minus lambda I. This is the equation. This is the equation is nothing but a characteristic polynomial. No, this is a characteristic polynomial that A minus lambda I. No, this is replaced by this is a polynomial is substitute, right? Now expand. Now after that, what we are going to do here, we have to write down the coefficients of like powers. We are comparing the coefficients of like powers. Means first we are going to go. First we are going to compare lambda to the power of n coefficient on both sides. Lambda to the power of n coefficient. Here lambda to the power of n coefficient means from this we'll get the lambda to the power of n coefficient. Lambda into lambda to the power of n minus 1 becomes a lambda to the power of n. So coefficient is minus I b naught, minus I b naught. There is no other terms here. No, similarly on the right side, lambda is a direct one. Lambda to the power of n coefficient is minus 1 whole to the power of n into I. If we want to take I, you can take I into I, right? Now after that, the next one. Next, to compare lambda to the power of n minus 1 coefficient. If we comparing the coefficients of like powers on both sides. So first we are going to compare lambda to the power of n term coefficient on both sides. After that, lambda to the power of n minus 1 coefficient on both sides, right? So on the left side, we'll get the two terms. Right side direct, minus 1 whole to the power of n into p1 into I. Actually, adjoint A into det A. What is the formula we applied there? A into adjoint A is equal to det A into I. So det A into I. So that is I is understood. If det A into I is nothing but det A, no. So sometimes we can take or no. If we need, we can take. Otherwise, we can leave. Right? Then here minus 1 whole to the power of n into I. On the right side, direct values you can take. On the left side, little bit we have to simplify. This is the lambda to the power of n minus 1 coefficient. This is lambda to the power of n minus 2 coefficient. This is a constant term. This is a constant term. So comparing the coefficients of like powers on both sides. After that, each term pre-multiplying of above equation successively means first equation is multiplied by a power n, second equation is multiplied by a power n minus 1, third equation is multiplied by a power n minus 2, and so on. Last equation is multiplied by I. Right? Pre-multiply means mundu. The b naught కి ముందు మనం multiply చేయాలి. Before you have to multiply minus a power n into b naught. Right? No, minus a power n into a into b naught minus a b1. Right? So like that you have to multiply. Now after multiplied with those matrices, so what we'll get minus a power n into b naught. Here minus 1 whole to the power of n into a power n into I is nothing but a power n. Right? So if it is a matrix is there, so no need to write down the I. If it is only the number is there, minus 1 to the power of n, single one, no? So you can write down the I, because we are showing on the right side also this is in the form of matrices. That's why if it is only the number, we write down I also. Because if it is a number, no, we thought on the left side is a matrix, on the right side it is a number. How it is possible? That's why write down minus 1 whole to the power of n into I. If it is a matrix existing, then no need to write I again, because it is a matrix only. So we are equating both of the matrices. Right? So like that multiply. So again we are getting these are the equations. After that, what we will do? Adding all these equations. If we observe on the left hand side, these values, so repetitions are there. One is a minus, one is a plus. One is a minus, one is a plus. Like that on the left side, all the values will be vanished. We'll get 0. Right? On the right side, if we take the minus 1 whole to the power of n is a common, we will get a power n plus p1 into a power n minus 1 plus p2 into a power n minus 2 plus pn. Right? Plus pn is equal to 0. On the left side, be 0. So this finally we will get, this is the equation. The equation is nothing but every square matrix satisfies its characteristic equation. Right? This is a characteristic equation. Whereas in place of lambda we got a. So it is satisfied by A. This is the Cayley-Hamilton theorem under matrices. Now, next theorem is Cayley-Hamilton theorem on linear operator, right? So, take the linear operator, same, similar to the on matrices only, right? Every linear operator satisfies its, this is a statement. Every matrix, they know every square matrix here, every linear operator satisfies its characteristic equation, right? Let T be a linear operator on a finite dimensional vector space. So it's a finite dimension kabatti. So we are defining the dimension as n. Therefore, dimension of V is equal to n, right? So let be, so for the linear operator, always we have to take the one standard basis. So B beyond the ordered basis of V. So here not the standard basis, it is the ordered basis, right? Ordered basis of V of F, and let A is equal to the matrix T with respect to B. So we are writing the A in the form of the linear operator like this with respect to the basis B, right? Now A is the same matrix A. After that, we are going to convert the linear operator, right? Next, take the characteristic equation. T minus, in place of A, what will get? T. So actually A minus lambda is equal to 0. Here T is nothing but we have to take the matrix only. That is a matrix T with respect to B. So here A we can take. After that, we can replace the T, right? No, this is the, we have to subtract from the lambda I. So we'll get the one characteristic polynomial. What is the characteristic polynomial? We got it here. This is a characteristic polynomial. In terms of the lambda, we got it. In terms of the lambda, we got the characteristic polynomial, right? Now what we want to show, we prove that the linear operator T satisfies the characteristic equation. Linear operator T satisfies a characteristic equation. If only this left hand side, we call it as a polynomial, and is equal to 0, it becomes a characteristic equation. No, same procedure. The elements of the matrix of A minus lambda are at most first degree. Cofactors of the elements are at most n minus 1th degree in lambda. Hence, adjoint of A minus lambda can be expressed as a matrix polynomial of degree n minus 1 in lambda. So this is a matrix polynomial of degree n minus 1 in lambda, whereas each coefficient as a matrix of n by n, that is n by n matrices, all are matrices of degree of order n by of order n, right? Now coming to the next, we know that A into adjoint A, this is always true. So we know from the matrices, one identity we have taken, A into adjoint A is equal to det A into I. A into adjoint A is equal to det A into I. Now from that, what we are going to take, now substitute all these values. We know, now after that, after this step, we have to replace A by A minus lambda I. We are going to replace A by A minus lambda I. Wherever A is there, just replace A minus lambda I, right? Then after that, what will write this one? So adjoint of A minus lambda I, already we got it. This is a polynomial in the form of the n minus 1th degree, right? Now this is initially we got a characteristic polynomial in terms of the A, characteristic polynomial of A of nth degree. So substitute that one into I, right? Now same. After that, comparing the coefficient of like powers of lambda on both sides. So we are comparing. So after that, pre-multiplying the above equations by these matrices. So we will get this. These are the equations we will get. Then after that, adding all these equations, on the left hand side we'll get 0. On the right hand side we'll get one polynomial in terms of the A, right? Now this is nothing but f of A is equal to 0. If we take f of, this is actually f of lambda, na characteristic polynomial. Now in place of lambda we got A. So this is nothing but f of A is equal to 0, right? So if we have f of A is equal to 0, then replace A is nothing but the matrix T with respect to B, right? The f of T can be written as T power n, T power in place of A take T, right? So this also can be written as the matrix T with respect to B, right? So for every matrix with respect to each term with respect to B, means T power n with respect to B, T power n minus 1 with respect to B. So which becomes the linear operator converted to the matrix like that, right? So this is nothing but A power n, P1 into A power n minus 1, P2 into A power n minus 2. Initially we have taken A is equal to matrix T with respect to B, right? This is f of A is equal to 0, which is 0 is nothing but the matrix 0 with respect to B, 0 matrix, that is 0 operator. So therefore f of T is equal to 0 of A means is replaced by T. So Tf of T means this one is equal to 0. Therefore, every linear operator satisfies its a characteristic equation. Right? This is a conclusion. In this session, what we have discussed, we discussed the following: Cayley-Hamilton theorem on a square matrix and a linear operator. Now, if we apply the Cayley-Hamilton theorem, remember, if we apply the Cayley-Hamilton theorem to the problem for finding the inverse of a matrix and higher powers of a matrix without using the routine methods.